Class 11 Chemistry, Chapter 4 Chemical Bonding and Molecular Structure. Hello students, this is your chemistry ma'am Archita ma'am. Today in this presentation I am going to discuss orbital overlap concept. Let's start the topic. Overlapping of atomic orbitals. Actually, the partial merging of atomic orbitals is called overlapping of atomic orbitals, which results in the pairing of electrons. The extent of overlap decides the strength of a covalent bond. In general, greater the overlap, the stronger is the bond formed between two atoms. Therefore, according to orbital overlap concept, the formation of a covalent bond between two atoms result by pairing of electrons present in the valence shell having opposite spins. When two atoms come close to each other, there is overlapping of atomic orbitals. The overlap may be positive, negative, or zero. Here it's shown the positive, negative, and zero overlap. The various arrangement of s and p orbitals resulting in positive, negative, and zero overlap is shown in the slide. The criteria of overlap as the main factor for the formation of covalent bond applies uniformity to the homonuclear, heteronuclear, diatomic molecules and polyatomic molecules. In the case of polyatomic molecules like methane, ammonia and water, the VB theory has to account for their characteristic shape as well. We know that the shapes of methane, ammonia and H2 molecules are tetrahedral, pyramidal and bent respectively. It would be therefore interesting to find out if these geometrical shapes can be explained in terms of orbital overlaps. Now let us see the types of overlapping. The covalent bond may be classified into two types depending upon the types of overlapping. It's a sigma bond and a pi bond. The type of covalent bond is formed by the end-to-end overlap of bonding orbitals along the internuclear axis. This is called as head-on overlap or axial overlap. This can be formed by any one of the types. The three types are being given. SS orbital overlap. In this case, there is overlap of two half-filled s orbitals along the internuclear axis. Next one is PP orbital overlap. This type of overlap takes place between half-filled p orbitals of the two approaching atoms. Next one is sp orbital overlap. This type of overlap occurs between half-filled s orbital of one atom and half-filled p orbital of another atom. Pi bond is given by the lateral overlap of the p orbitals. This is example of pi bond. Now we would see this hybridization. In order to explain the characteristic geometrical shapes of polyatomic molecules like CH4, NH3, H2, etc., Pauling introduced the concept of hybridization. According to him, the atomic orbital combine to form new set of equivalent orbitals known as hybrid orbitals. Unlike pure orbitals, the hybrid orbitals are used in bond formation. The phenomenon is known as hybridization, which can be defined as the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. Now, if we talk about the type of hybridization, there are various types of hybridization involving s, p, and d orbitals. Like sp hybridization, the suitable orbital for sp hybridization are s and p. If the hybrid orbitals are to lie along the z-axis, each sp hybrid orbital has 50% s character and 50% p character. Such a molecule in which the central atom is sp hybridized and linked directly to two other central atoms possesses linear geometry. In sp2 hybridization, there is involvement of one s and two p orbitals in order to form three equivalent sp2 hybridized orbital. And again in sp3 hybridization, this type of hybridization can be explained by taking the example of CH4 molecule, in which there is mixing of one s orbital and three p orbitals of the valence shell to form four sp3 hybrid orbitals of equivalent energies and shape. Now let us consider example of formation of Sf6 molecule. In Sf6, the central sulfur atom has the ground state outer electronic configuration of 3s2 and 3p4. In the excited state, the available 6 orbital, that is 1s, 3p and 2d, are singly occupied by electrons. These orbitals hybridize to form 6 new sp3d2 hybrid orbitals, which are projected towards the 6 corners of a regular octahedron in Sf6. This 6 sp3d2 hybrid orbitals overlap with singly occupied molecule orbitals of fluorine atom to form 6 Sf sigma bonds. Thus, Sf6 molecule has a regular octahedral geometry as shown in the figure. Now let us see the formation of hybridization in C2H2. In the formation of ethyne molecule, both the carbon atoms undergo sp hybridization, having two unhybridized orbitals, 2py and 2px. One sp hybrid orbital of one carbon atom overlaps axially with sp hybrid orbital of the other carbon atom to form Cc sigma bond, while the other hybridized orbital of each carbon atom overlaps axially with the half-filled s orbital of hydrogen atoms, forming sigma bond. Each of the two unhybridized p orbitals of both the carbon atom overlaps sidewise to form two pi bonds between the carbon atoms. So, the triple bond between the two carbon atoms is made up of 1 sigma and 2 pi bonds. Molecular orbital theory. The electrons in a molecule are present in various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. While an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nuclei depending upon the number of atoms in the molecule. Thus, in an atomic orbital is monocentric while a molecular orbital is polycentric. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital while the other is called antibonding molecular orbital. The kind of bonding and antibonding is being shown in the slide. Now, if we are going to talk about the bonding of the hydrogen molecule, it is formed by the combination of the two hydrogen atoms. Each hydrogen atom has one electron in one s orbital. Therefore, in all there are two electrons in a hydrogen molecule which are present in sigma 1s molecular orbital, and the bond order for the hydrogen we get is 1. Now here we could see two types of molecular orbital. Actually, the only difference is in the orientation, in the arrangement of the p orbital. This one and this one. If you see here, pi orbital is of low energy than sigma orbital, and here sigma orbital is of lower energy than the pi orbital. So, in the first diagram, this diagram is common up to N2. Means boron, carbon and nitrogen is going to obey this kind of molecular orbital, and after that oxygen, fluorine and neon is going to obey the second kind of molecular orbital.